Hello everyone, this is Sherry Sahebi and we are actually learning data mining. So today we are going to talk about kernels and kernel methods. So first, take a look at why we need kernels and what kernels are. Whatever we have learned so far, or the analysis that we have learned so far, were linear analysis. So for example, we have learned PCA and SVD, and we have seen that they are built based on linear combinations of our data matrix rows or columns. So they are basically finding if there is a linear combination that is existing between our data points. So it finds linear relationships. So for example, we had this example in SVD that we said if our data is represented in 2 dimensions, but there is a one-dimensional representation like a line that we can show all of our data on it without being too precise, then we are going to go towards this linear representation that is one-dimensional. So this captures a linear relationship between our data points. So if our data points, for example, they looked like this, if they were in a circle, then a PCA couldn't do anything for us because we couldn't find a lower dimensional representation that uniquely can represent our data with minimal error. If we choose this axis versus this axis or this other axis to represent our data, it really doesn't change our representations because we are going to lose the same amount of information. The variance of our data in all directions are the same. So it's really, there's no difference between the first axis and the second axis and the third axis. Or suppose that our data looks like a swirl. So there is a pattern in this swirl because we, with our eyes, can see that there is this swirl pattern in it, right? It's two-dimensional, it looks like a swirl. But if we apply PCA on that, it cannot understand this swirl pattern in our data because PCA can only look at linear relationships in our data points. So again, it tries to map our data into one line, lower dimensional representation, by projecting our data on the line. And again, it doesn't really matter which direction we choose because the variance of our data in all of these directions are going to be the same. So sometimes we have a nonlinear relationship in our data or nonlinear pattern in our data that we cannot capture with the linear methods that we have learned so far, or we are going to learn later on. For example, suppose that we need to distinguish, we need to have a classifier to distinguish between positive and negative examples. So we haven't learned about classifiers, but we are going to have this example that, for example, if I have cats, so there is this weight and height of my animals as my two axes or two characteristics. And then I have this relationship between weight and height of cats. So these guys, the blue ones, suppose that they are cats, and the green ones are dogs. Now, in linear classifiers, what I do is that I find a line that can separate these two classes from each other, that can separate dogs and cats from each other. But if I want to have a linear classifier to separate this kind of data, now suppose that my data is not like what we have seen. Suppose that the relationship between weight and height is like this for cats and dogs. So it's kind of a circular relationship. So the ones that are in the middle are cats, and the ones that are around are dogs. Now, I cannot really find any line that can perfectly separate my cats and dogs from each other in this case. So my linear classifiers won't work. What I need is a classifier that is nonlinear. For example, if I draw this circle, it can separate cats from dogs in this example. So one reason that we need kernels is that we have a nonlinear relationship in our vector data that, or in our data matrix that is numerical, and we want to be able to capture that nonlinear relationship with the tools that are built for linear relationships. Okay. And the second reason is that also sometimes our data is not numerical. We cannot represent our data easily with numerical features. And so our data is not a vector-like data, but there are, although there are not features that are numerical that can be defined on our data, but we can define similarity between our data points. So what do I mean by that? Suppose that our data is a set of strings, and if I have two strings, so for example, I have a string that is coat, and then I have another string that is cat. What I can do is that I can represent the similarities between coat and cat easily. For example, I can find the edit distance between these two. I can say, okay, I can go from coat to cat by removing an O, right? So I can say, okay, there is one insertion or one deletion distance between these two, otherwise they are similar to each other. But it is really difficult to have a vector representation of coat or cat that also has this order in it. So I can have this vector representation that says A, B, C, D, etc. until Z, that coat has one C in it, one A in it, one T, and one O, right? But, and the rest is zero, like that kind of a vector representation. But the difficulty with this one is that it doesn't consider the order that are between my alphabets that are presented in code, right? So sometimes our data is non-vector. It can be image, it can be string, it can be graph. So we cannot really represent our data points in a vector format, but what we can do is that we can define some similarities or distances between our data points. So we don't have any coordinates for each of our data points, but we can represent our similarities. And what we want to do is that we want to use the methods that we know, the linear methods that we know that can work with vector data, to be able to work with these kinds of data for us. So basically, two reasons. One is that sometimes our vector data has a nonlinear pattern in it, and we want our linear tools to work for that. And the second reason is that sometimes our data doesn't have a vector form, but we have some similarities or distances between our data points, and we want to use those information to be able to find patterns in our data. So the kernels are going to do that for us. Kernels are going to transform our data in a way that all the operations that we have done before in linear spaces can be done only according to the similarities between the data points. And also, they are going to transform nonlinear relationships such that the linear tools can work on them. Okay, let's see how they are going to do that. So with kernels, we have a kernel representation of our data. So if I have a data point X, I can define a mapping from this X to phi of X. So X is our original data in our input space, and phi of X is a higher dimensional, usually higher dimensional feature space. Okay, and this way we can take care of the nonlinearity in the data, and also we can provide some kind of a vector space for the data that is non-vector, and we are going to see examples of that. Then when we mapped our data from this input space to a new, possibly high dimensional feature vector space, then we basically can use our linear tools in this new feature vector space, which phi of X is defined on, and our data is going to be represented with linear relations. Now, so far, we have learned that working in high dimensional spaces are difficult, but now here in kernel representation, what we are saying is that we want to map our data to a higher dimensional feature space. Wouldn't that make our work more difficult? Well, that's how kernels are going to help us, because they have this trick that instead of working with these new coordinates in the new representation in this higher dimensional space, they work based on the similarity between data points. And this similarity are calculated not in the higher dimensional space, but they are calculated based on the lower dimensional representations. So this may seem a little bit weird right now, but as we see examples, we are going to see how this can work. So let me just give you a simple example. So on this image, this plane is our X. So our data points represented in a two-dimensional space. So this is one dimension, x1, axis x1, and this is another one, axis x2. So we have two features in our original space. And you see that some of the data points are red, like these guys, and some of them are blue. And the red and blue, they are kind of mixed together. They are not exactly separate, completely separate from each other. Now, what we can do is that we can have a mapping from our X to a phi of X that is, in this example, three-dimensional. So this is our phi of X. You can see that it's a three-dimensional object that has, like, similarly, it has some, let's call it phi of X1, and then phi of X2, and phi of X3. So in this three-dimensional representation, or maybe we can actually say phi 1 of X, phi 2 of X, this is actually more accurate, and phi 3 of X. Okay. So in this new representation, we can define phi of X, this function, in a way that our red data points and the blue data points are more separated from each other. So let me give you another example. Suppose that our data are like this weight and height that we had. Height. And we had two types of data points. These were dogs. And these were cats. So in this two-dimensional space, we cannot find a line that separates cats and dogs from each other, right? Whatever I want to do, it's going to look like a higher dimensional polynomial, right? This is a circle. This is a curve that can separate my cats and dogs from each other. But assume that instead of height and weight, I represent the same data in this way. I can say I represent them by height square, weight square, and height multiplied by weight. Or let's do something else. We can, for example, represent our data this time. Instead of these three, we can represent our data according to height, weight, and the R, that is basically the distance between my data point from one point in the middle. So for example, it's going to be height plus weight, height square plus weight square, if this is on 0, right? Square root of height square plus weight square. Okay, how does this help me? So we can see from this image that the more R is, the more distance from this center I have, the value of R is going to be higher, right? So in this new three-dimensional space, the first dimension is height, the second dimension is weight, and the third dimension is my R. What I'm going to have is that my dogs, the green points, are all going to have a higher R for me compared to my cats, right? Because they are far, compared to cats, they are farther from this point. So although I could not separate the cats and dogs with a line in this original space, I had a curve. Here, I can use a plane, which is linear, to separate my cats and dogs from each other. Okay, so basically we are transforming our data using this phi of x according to the original features. So phi of x is a function of original features such that we, in this new higher dimensional representation, we have a linear relationship in the data, or we can find separate our data using linear tools that we have, and it's going to be easier to work with. Another example is the sequence-based features. So this x to phi of x, it's not necessarily a nonlinear relationship like this one that we had. Any kind of representation from the feature space, from the input space to feature space, can be considered as phi of x. So suppose that we have a data set of DNA sequences that are defined based on this set of alphabet, A, C, G, and T. So for example, we can have a sample that is G, C, C, A, T, T, A, right? This can be a data sample for us. Now, if we want to represent our sequence in a vector space, similar to what we did with the code, we can define a vector representation that has A, C, G, and T as our features. And basically, A is going to be the probability of seeing A in my data, and C is the probability of seeing C, etc., etc. So this is going to be my phi of x. My phi of x is going to look like this. It's going to be a vector. In the first place, it's probability of A, second place, probability of C, etc., etc. Now, what is the probability of A, for example, in this sequence that I have? I can see that the length of my sequence is 1, 2, 3, 4, 5, 6, 7. Okay. And I can see that, let's call this M, which is the length of my sequence. And I can see that there are 2 times that A is defined here. So my vector representation of xi, phi of xi, is going to look like this. I have 2/7 for A and 2/7 also for C, because I can see that 2 times, 1/7 for G, and 2/7 for T. So this is another way that we are representing a string in vector space, but it is going to lose some information anyways. All right. Now, for nonlinear features, similar to the example that I showed you, the mapping phi is going to be nonlinear. So our input space in the example that I showed you was weight and height of animals, right? So our input space already is a vector that can be defined like this. It's x1 attribute 1 and x2 attribute 2 transpose that belongs to r squared, because it's a two-dimensional vector input. Now, we can map this into nonlinear features by using nonlinear function phis. So, for example, if we want to map it to a quadratic feature space, like what we have done there, we can say the phi of x is going to be a new vector that the first feature of it is x1 squared. The second feature of it is x2 squared, and the third feature is square root of 2 multiplied by x1, x2. So you can see that we are going from a two-dimensional space to a three-dimensional space, because we have 3 new features, right? x1, x2, x1 squared, x2 squared, and this multiplication between x1 and x2, right? So we are going from lower dimensional, which is 2, to a higher dimensional, which is 3. So an example of that would be that we have a data point. In the input space, it's represented by 5.9 and 3, and we can map it to this vector. So 5.9 squared, which is going to be equal to 34.81, 3 squared, which is going to be 9, and square root of 2 multiplied by 5 multiplied by 5.9 multiplied by 3, that's going to be 25.03. After we move our data from the input space x to the new feature space phi of x, then we can apply the linear analysis that we had in this new feature space. So similar to what we had here, we had weight and height, and our data were in the two-dimensional input space, and then we moved it to a three-dimensional feature space, and then we didn't need a curve to separate our data. We could just do it with a linear tool that we had, which is just a plane. So the curve was quadratic, but then here we have a plane. All right. So basically, what we are going to be having is going from a linear method to be able to apply and find patterns in nonlinear data only using kernels. So we have an input space that is R to the d-dimensional input space. We apply a transformation, usually nonlinear transformation, on the input space, and we get to a new m-dimensional feature space that usually m is larger than d, sometimes equal to d, but usually larger. And then we can use linear tools to make sense of this data that we have. But again, we said that working with high dimensional space is difficult, right? That's what we have said before. Additionally, sometimes transferring our data to this new high dimensional space is really expensive. So generation of phi of x for all of our x's is expensive. And sometimes it's even not feasible. So you will see later on a higher dimensional kernels, like infinite dimensional kernels, that basically it's not feasible to apply that on our feature data points in the input space to get to the feature space. So what we can do instead is that instead of working on phi of x's directly, so in the new feature space, what we are going to work on is the inner product between our data points in the feature space. So basically, what we will say is that instead of working with phi of x, we are going to be working with the values phi of xi transpose phi of xj, the inner product between the mapping of data point xi and data point xj, and we call this k of xi and xj, k for kernel. And then if we define this for all of our mapped data points, we are going to get to a kernel matrix that's basically defined by k between x1 and x2, x1 and x3, x1, 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 x2, x1, x3, etc., etc. So if we have n data points, we are going to have an n by n matrix that defines the relationship or the inner product between n data points, each pair of n data points that we have. So that is going to be an n by n kernel matrix. And this way, instead of working with phi of xi transpose phi of xj, we are going to work with the similarity, kind of similarity between them, that is, that we call it kernel, with the kernel matrix. So we won't need phi of xi and phi of xj anymore. But then you would say, okay, how come this is possible? Because if we don't have the phi of x, so we said we are going to work with the kernel or the similarity between phi of xi and xj, because it's sometimes not feasible to work with phi of x because we have infinite dimensional phi of x transformations, or sometimes it is very expensive to get to phi of x. But if that is expensive, the kernel calculation should be also expensive, right? Because we are defining kernel according to inner product between phi of xi and phi of xj. So how come we can get to this k without this phi of xi and phi of xj? That is what the point of kernels are. That is what is called the kernel trick that makes all of this to be possible. Now, what is the kernel trick? The kernel trick is like this. We can have some specific phi of xi, phi of xj's, that when we calculate phi of xi transpose dot phi of xj, the kernel is actually going to be defined according to the original features of our data points in the input space. So kernel is a function of our original features. We don't need to explicitly calculate phi of xi and phi of xj to calculate the value for the kernels. We just need the original features of xi and xj in the original input space. And this is the way that we can work with kernels. So kernels are the similarity between our data points in the new higher dimensional data, but we can calculate this similarity based on the features that represent our data in the original feature space. So this is a function in input space. It's a function of input space, but the value that it is going to give us, the dot product, is equal to the value of the dot product in the feature space, in the new high dimensional feature space. Okay. So that is the kernel trick that we are going to have. And then we are going to see these kernel properties soon and see what are these functions that can do this for us. So before that, let's see some common kernels. What are the common kernel functions that we have? The first very simple common kernel is the linear kernel. So basically, in linear kernel, our phi of x is x itself. So we can say phi of x. For example, if I say phi of x is equal to x, x the vector of my feature representation, I get the identity kernel, which is basically a specific kind of linear kernel. So if I want to calculate the kernel function between two data points, x and y, which is equal to phi of x transpose dot phi of y, that is the definition of kernel, right? Since we know that phi of x is equal to x, so it's going to be x transpose dot. Now phi of y is equal to y, it's equal to y. So with this linear kernel, with this linear identity kernel, what we have is that the kernel between x and y data points is actually equal to x transpose y. Okay. Let's see an example. So this linear kernel basically doesn't really take our data into a new, different feature space, but what it does is that it makes us be able to calculate everything according to the dot product between our data points instead of the data points themselves. So suppose that I have a data set that is 5 by 5. Okay, so this is my data set. I have 5 data points. Sorry, not 5 by 5, 5 by 2. So I have a 5 by 2 data set D, meaning that I have 5 data points, x1, x2, x3, x5, and 2 features. So let's say this is x1 and x2. For example, I can look at my x1 here, and it's, for example, 5.9 and 3. I can look at my x2 here, and it's 6.9 and 3.1. All right, so this is basically my representation of my data points, my 5 data points in the original 2-dimensional space, input space that I have. Now, if we apply the linear kernel on that, what I can do is that I can calculate the k kernel between x1 and x1 itself. I can calculate the kernel between x1 and x2, the kernel between x1 and x3, etc. Can do that for x2 also, x2 between x2 and x1, between x2 and itself, right? So this way, from my 5 by 2 dataset D, I can get to a 5 by 5 kernel matrix that defines the similarities between my data points. Now, because we are working in the identity kernel, I know that the k between x and y is equal to x transpose y, right? So for example, if I want to calculate the kernel between x1 and x2, it is equal to x1 transpose x2, right? Now our x1 is what? It's 5.9 and 3, right? And my x2 is 6.9 and 3.1. Now, because this one has a transpose of transpose is itself, this is going to be a transpose. Okay, this dot product. So what is the value? It's actually equal to 5.9 multiplied by 6.9 plus 3 multiplied by 3.1, which is equal to 50.01. And that is the kernel between x1 and x2. So here in this matrix, I'm going to have 50.01. Similarly, I can have this for the rest of combinations. So I get a mapping from the input space D into the input space itself, because phi of x is equal to x, but I get to this kernel matrix. So this is the simplest kernel that one can have. But then let's go see a little bit more complicated kernels. The second kernel that is very popular is the polynomial kernel. Now, the polynomial kernel, it has a degree, a polynomial degree, which is called Q. And it can be of 2 types. It can be homogeneous or inhomogeneous. So in the homogeneous kernel, what we have is that phi of x, because the kernel is equal to the kernel between x and y is equal to phi of x transpose phi of y, and it is defined like this: x transpose y to the q. So the identity kernel that we saw above, it was just X transpose Y. The kernel between X and Y was just X transpose Y, right? It's a special case of the polynomial kernel when Q is equal to 1. The degree of polynomial is equal to 1. So this is when we have homogeneous kernel. In the non-homogeneous kernel, in addition to this, we are going to have a constant added to it. So in homogeneous, the kernel between X and Y, which is equal to, again, phi of X prime phi of Y, is defined like this: C plus X transpose Y to the Q. Okay? So there is a constant C that is added to the polynomial kernel. Just note that, see, here we are defining K, the kernel function, according to the data points in the original input space. We are not defining K according to phi of X and phi of Y separately. I mean, always kernel between X and Y is going to be equal to phi of X transpose dot phi of Y, but we didn't say what phi of X is or phi of Y is. We directly define the kernel according to the original input space features. So the most commonly used polynomial kernels are the linear one. When Q is equal to 1, we have seen that. Now, if it is not identity, we can have like the inhomogeneous that we have a C here, or the quadratic one in which the degree is 2. Okay. So we said that our polynomial kernel is defined according to input space like this, right? But can we actually figure out what phi of X and phi of Y are in this kind of kernel? Can we find the mapping itself? Let's look at it for the Q equals to 2. If I have Q equal to 2, then the K between X and Y, suppose that we are looking at the homogeneous, is equal to X transpose Y squared, right? So suppose that I am having my X and Y in a two-dimensional space, right? So suppose that X is, it belongs to R squared, Y is also belonging to R squared. So suppose that X is basically X1, Y, X1, X2, and Y is also basically X1, X2, Y1, Y2, right? Can we actually get to what is the phi of X and what is the phi of Y that can generate our polynomial kernel here? Right? So let's see an example. If we have a two-dimensional space, this is the example that we had, with data points X and Y, we want to calculate the homogeneous quadratic kernel between X and Y. So let's see, first of all, what is the value of this kernel going to be? So again, our X is two-dimensional. So X is X1, Y1, X2, sorry. And Y is also two-dimensional, values Y1, Y2. Now, we are homogeneous kernel, so K between X and Y is equal to X transpose Y squared. So let's see. What is X transpose Y squared in this case? It's going to be equal to X1, X2, Y1, Y2 squared, right? So C is also equal to 0, right? So basically, it's going to be equal to X1, Y1. This is the dot product that we have. X2, Y2, and then squared, right? Okay, so now these are all scalars, and we have the summation of two scalars and the square of them. So it's going to be equal to the square of first one, x1 square, y1 square, square of the second one, x2 square, y2 square, plus multiplication of first one and second one, right? So x1, y1, x2, y2, and two of them, right? So this is the value of kernel between x and y that we are going to get for these two data points in the original two-dimensional space. But also we know that this is equal to phi of x transpose phi of y, right? What is the phi of y or phi of x? What is this function phi that if we calculate this, we are going to get to the same value like that? So first of all, it can be three-dimensional, right? We have three different summations in our case. Now, if I have phi of x is equal to, the first one is x1 squared, and then for phi of y, I'm going to have y1 squared there, right? So then x1 squared and y1 squared are going to give me the first term here. For the second term, if I have square root of x1, x2 for phi of x, and by symmetry, square root of y1, y2 for phi of y, multiplication of these two is going to give me this second term. And for the third new dimension or third feature in the feature space, if I have x2 squared for x and y2 squared for y, symmetrically, I'm going to get to the third feature when I multiply phi of x and phi of y, right? So let's double check. Let's calculate phi of x transpose dot phi of y according to these two new ones. I'm going to get this is equal to x1 squared, y1 squared plus square root of 2 to the 2 x1, x2, y1, y2 plus x2 squared, y2 squared. Okay, see? So this phi of x dot phi of y is equal to this kernel value between x and y. So basically we have seen in this example that when we have a homogeneous quadratic kernel that we are defining like this, so the homogeneous quadratic kernel that we are defining like this, we can figure out what phi of x and phi of y were, that we could get to the kernel between x and y to be x transpose y squared. X transpose and y both are in the original input space, but we could figure out that the new feature space that generated this value for the kernel is actually this three-dimensional space. Now, looking at an example of it, we can see it here. So our original two-dimensional space here x1 and x2, and then we have these points represented in x1 and x2 space. And again, suppose that we have two classes, we can separate them with this curve. And then if I transform x1 and x2 into z1, which is phi1 of x, and z2, phi2 of x, and z3, which is phi3 of x for me, and z1 here is x1 squared, z2 is square root of 2 multiplied by x1, x2, and z3 is x2 squared for each of our data points. Now I can represent each of my data points here in this new space. And then we will see that we can separate the two with just a plane, which is a linear separation. Okay. Now, what happens if our polynomial kernel has a higher degree than the kernel of degree q between data points x and y in the original input space, which is equal to phi of x transpose phi of y, phi of x and phi of y are in the new feature space, the value is going to be c plus x transpose y to the q. So the value of their distance or dot product in the feature space, in the new feature space, is going to be equal to this in the original input space. Now, how can we actually open this up and see how it is going to look like? This, it has a formulation that we can basically use the binomial expansion for that. We can rewrite this as k equals to 1 to q summation of selecting k out of the q degrees. Now c to the q minus those k, so q minus k of the degree is going to the c, and x transpose y, the k of the degree is going to our x transpose y. So for example, for the polynomial with degree 2 that we have seen before, if we follow this equation, it's going to be selection of 0 from 2, c to 2, x transpose y, 0, plus selection of 1 out of 2, c, x transpose y, plus selection of 2 out of 2, c to 0, x transpose y, 2, right? Which is equal to C2 plus 2C x transpose Y plus x transpose Y squared. And you can do that for higher orders also. So this was the polynomial kernel. Now, Gaussian kernel is another famous kernel that we can have. It's also called Gaussian radial basis function, or RBF kernel. So in that, the k or kernel value is defined like this. It's exponential of x minus y squared divided by 2 sigma squared, which sigma is a parameter that defines the spread or standard deviation, for example, of our data. Now, what is the shape of this kernel? We can see that for two data points, x and y, the more distance they have from each other, so the x minus y is going to get larger, right? And because we have e to the minus something that is related to the distance, then the value of kernel is going to be smaller. So the farther x and y are from each other, the value of the kernel is going to be less and less. Now, because there is this exponential function there, the rate by which the value of kernel is going to get less, depending on the distance, is going to be an exponential rate. That's why it looks like the whole kernel function looks like a Gaussian distribution function that we have seen before, right? And also to define how far is far, we divide based on this spread parameter. Now, because we have this exponential shape, then we are going to have a cone-like shape for our kernel, or basically the whole value of the kernel is going to follow a radial, like a circular kind of shape that within each radius, it's going to get less and less and less. So, for example, if you want to calculate the kernel between each data point and itself, x and x, because x minus x is going to be 0 and e to the 0 is 1, so the kernel between each data point and itself is going to be equal to 1. So the maximum value of this kernel is going to be 1. And then as we go farther from x, the value is going to be less and less, inversely related to the distance between the other data points and x. So this kernel is one of those ones that we cannot directly define the feature space phi of x for it because it has infinite dimensionality. So in this kind of kernels, no matter how much we try, getting to phi of x, because it's infinite dimensional, it's going to be difficult. Like here, we could get back to phi of x, right? But here, phi of x is going to be infinite dimensional, so it's going to be difficult to figure out. So we have to still work with k.